Hello everyone, welcome to this KANPUR-NPTEL online course on space environment and its effects on orbital spacecrafts. So, these days we are discussing the plasma environment, and in the last class I discussed what is the the phenomena by which the spacecraft charging happens. We compared it with the the capacitor charging and compared it with a water bath and the incoming water, then outgoing water. Then we start discussing the probe theory, that is the Langmuir probe, and today we will continue with the same topic in a little bit more detail. So, we will consider the different probe geometry, considering cylindrical geometry, then spherical geometry, the plane geometry. So, as I already told that the spacecraft you can assume it is like a probe inserted in a plasma medium, that is where the charges are flowing or charges are moving with the respective kinetic energy. So, we will take that is what is called the orbit limited. So, orbit limited, I will tell that when in this especially this orbital plasma, that the density is, we can consider the density is it is relatively it is lower, and as a result of this interaction between the particle to particle interaction is less. So, in that case the motion of the particles in the space plasma it is governed by the angular momentum. So, this is called the orbit limited the regime or orbit limited angular attraction. So, as already you have seen that this whenever you insert a probe, so that probe will naturally it will accumulate more number of electrons as a result of that lower mass, because the electron is having lower mass. So, it will have the higher velocity. But after when the electrons are accumulated, then it will repel the further electrons incoming, and it will attract the positive ions. So, it is shown here exactly. If you can see here, now the electrons have been deposited, you show here these electrons are deposited. So, these are all the electrons deposited here. So, it is repelling the electron, and whereas it is attracting the ions. Now, we will see a little bit about that is how this works. There is this attraction. So, as I said that charged particle it repels the plasma charges of the same sign and attracts those of the opposite sign. And already we discussed what is the plasma sheath. So, this surrounding this spacecraft the environment is non-neutral, and that non-neutrality will continue up to some length. So, that is called the Debye length. So, you can consider a sphere within which a sphere surrounding the spacecraft within which the medium is non-neutral, and outside it, it is the neutrality of the plasma is there, where we assume that it is a reference for the potential. So, you consider it is the phi is equal to 0 there. So, as what I said, the plasma density inside the sheath is different from that outside, because inside it is non-neutral. Now, the mean energy of the charged particles is shifted by the repulsion and attraction, because there is an attraction of q phi e. So, whatever this energy of the particle is there, so that it will be whatever is inside the sheath, that the particle the energy it will be modified by this quantity. So, that is why this term is there. And this material, especially the spacecraft charging material, whatever I am discussing, that I have adopted from this book. There is the fundamentals of spacecraft charging and spacecraft interaction with the space plasma by Shu T Li. So, again this shift depends on the magnitude of the repulsion and attraction, means what is that the what is the potential developed, what is the field inside the sheath. So, that will decide what is the shift in the energy. So, now we will consider the Langmuir probe and we will consider the shape is a sphere. So, this equation what we are going to derive, it is useful for describing a simple current balance model of the spacecraft charting for situations where the geometry is isotropic. Sphere means we are considering a isotropic geometry. So, orbit limited attraction, already I said what is the orbit limited attraction. So, let us consider a particle, it is moving at a velocity v from an infinite distance r is equal to infinite. So, infinite distance means there the potential energy r is equal to infinity, that will be equal to 0. Towards the and it is moving towards the vicinity of a charged spherical spacecraft which attracts the particle. As for example, as we have already shown you, if it is negatively charged, then will attract a positive ion. So, assume a positive ion is moving from infinity, at infinity its potential energy, that is the force of attraction or the energy or the potential energy is 0 there. Now, what will be the sum and the sum of the kinetic energy and the potential energies of the particle is constant. So, this is the conservation of energy, it has to be constant and we can give it at any distance. So, this is at any any distance r, at any distance r we can write this equation. So, this is the kinetic energy V r's and this is the potential energy q into phi r. So, which has to be equal to this what is b here, b is the velocity when r was infinity. Okay. So, next what we will do, so here it is the q is the charge of the particle being attracted. So, if it is an electron, so q will be, it will be minus, we will write it E, and where E is the elementary charge of an electron, and for a positively or the singly charged ions. So, q I will be equal to E, the charge of the the electron and the positive ion will be the same. For a negative potential, now suppose phi is negative, then the sign of this phi and E will be positive, while q I into phi will be negative. So, the kinetic energy at infinity, it equals approximately to the mean thermal velocity for an equilibrium plasma. So, this is the condition. So, this is the energy, we can write the kinetic energy is equal to k T, where there is no the force of attraction is not there, or there is no the interaction between the particles. So, I can write this equation. Now, the angular momentum. Now, what is angular momentum? Angular momentum is when a particle is it is moving, suppose it is moving in a circle, a particle is moving in a circle, let us write a circle. So, it is moving in a velocity v, then this angular momentum is given by p cross r. What is p? P is the linear momentum. If this particle is having mass m, so it will have m b r dash. And for circular cases, this is the r vector and this is the v vector. So, it will be m b r. So, we can write it m b h is equal to m b a, where a is the radius of the sphere. What is h? We will explain in our next slide. So, this is the equation we wrote. So, we do not know what is h, I will now explain. What is a? A is the radius of this sphere and the velocity when it is the tangential velocity when it reaches the spacecraft surface. So, what is h here? H is called the impact distance and it is measured from the center of the sphere to the straight line of travel, and a is already I said it is the spacecraft radius, and this is b a, this is the velocity b a of the particle when it touches tangentially the spacecraft at r is equal to a. So, now let us try to understand what is this impact, the impact distance. So, now you consider this is your spherical spacecraft, or it can be a cylinder also, we will say that. So, suppose the particles are moving. Now, this particles are, whenever the particles will enter to this the electric field of this spacecraft, what is, or you can assume like that, when it is entering the plasma sheath, then what will happen? This will exert a force, that is the angular momentum, and it will have an angular momentum, and it will be bent towards the spacecraft, and it will strike the spacecraft. Now, it again depends what is that height it is coming. Suppose it is coming from a greater height, from the, you can say h is, you can just consider another some capital H, and it is something is coming from there, and then though it will be bent, but it will not come to the the spacecraft. So, what h is defined, what is the h? H is it is this maximum vertical distance h, beyond which an ion trajectories would miss the sphere. So, you see this one is beyond h, this trajectory is beyond h. So, it is missing to reach to this sphere. So, this is called this is the concept of the impact height. So, we have to here do a little bit. So, what we have written that equation. So, first of all we will write this this equation for this particle density. So, I will write it. I can write this expression already I wrote previously, that I can write any at distance r. So, this is equal to n 0 e to the power minus q e, then phi divided by k T B. Similarly, I can write it for n I also, similar expression, only q e will be replaced by q I. And then I can write my that is the current or the current density. So, I e I can write in terms of I e 0 e to the minus phi e q e phi divided by k T B. So, this should be in bracket. Okay. So, now what we have written? We have written that is the total energy, that is the sum of the kinetic energy as well as the potential energy is constant, and it will be equal to the what is the kinetic energy when we are considering that the particle was at an infinite distance from the spacecraft. So, I will write that. So, at any distance the kinetic energy is m b square by 2 plus q, that is phi r. So, that is equal to m b square by 2, and that is equal to k T. So, I can write this m b square by r by 2 is equal to k T k T minus q phi r. Okay. Now, what is my m b? So, m b h is equal to, so I can write from this expression, that that V A by V, this is equal to h by A, I can write, or then using this now what I can do using this equation, and another equation I can write, that is the same equation if I write. So, at I can write it m b square by 2 is equal to k t, because this k t is this phi r is 0 at r is equal to infinity. So, from these two equations I can write this using these equations. So, you divide this by this. So, you will get so B A, and I can use this equation. So, I write that m b so B A by V is equal to, so I can write it B A by V will be equal to 1 minus k t phi r divided by k t. So, I have taken this side. So, it will be, when I divide it by 80, so it will be 1 minus q phi r by k t. Okay. So, then it means H A is equal to A into 1 minus q phi r by k t. So, this is the derivation, we will show it. So, this is the way it is derived. So, this already I derived it, whatever I wrote this equation. So, this is the equation I wrote. So, I can write it here, H is equal to A by this. Now, the velocity B A at r is equal to A, then I can write it B A by, since B A by V A is equal to was this. So, I can write B A is equal to B into 1 minus q. So, same expression I can put it here. Now, we will consider the current collection in the spherical geometry. So, in so this we will consider, this is now a sphere. So, it is having, it is isotropic. So, it is spherically symmetric. So, the current collection we can write it like this. So, it will be now you see only those particles. So, this is my, this I should consider, this is my H, this is H. So, now you can consider a sphere with this radius as this is H, I will consider from here it is H. So, in that case what it will have, so that sphere will accumulate the charges. So, I can write the current the collection by this expression, where this is the surface area 4 pi h square is the surface area, then it is the density, and this is the charge per unit particle, and this is the velocity. So, n is the plasma density, as I already said. So, I can use now substitute the h value here, and the V A I can substitute, and I can write my I phi A expression will become like this. So, this is the I phi. So, which I can write in the form I phi is equal to I 0. So, how I have got it? By putting phi is equal to 0. So, what if phi is equal to 0 means? It is just before or at the time, or just before this spacecraft got charged. So, that means this spacecraft is not charged. So, phi is equal to 0. So, this above equation is called the orbit limited current collection formula for spherical spacecraft. Okay. So, for when the spacecraft is not spherical, it will have a complex geometry. We will show what is the technique we use it, but considering it is a very ideal spherical condition, you can find this is the current collection formula by using the probe theory. And this is called actually this is called the Langmuir probe formula for current collection in the orbit limited regime. Already I said what is the orbit limited regime, where the angular velocity, that is the moment of that charge is governed by the angular moment. Okay. So, this formula was discovered by Mott, Smith and Langmuir. Now, we will consider the current collection by the cylindrical geometry. So, we will use the same formula, only the current collection that thing will be different. So, here the cylinder is having the cylindrical, there is a symmetry about the z axis. So, this is here in this case we are considering a cylinder. So, the current collected by a cylinder will be given by this. So, what is this? This is the circumference. This is the circumference. Again here you are considering that impact height. Impact height means the maximum height below which the charges will be collected by the spacecraft. So, this is the h. This is h I am considering here, and again what is the n? N is the plasma density and q is the charge per unit the plasma particle, and this is the velocity, and L is the length of the cylinder which you are considering. Okay. So, you are collecting, this is the collecting surface. Collecting surface is the surface area which is circumference multiplied by the length of the cylinder, and this h already we have derived this equation for h, the impact height. So, impact height, it is a function of, first it is the spacecraft radius. So, what is A? A is basically the radius of the sphere, or here in this case it is the radius of the cylinder, in the other case it was the radius of the sphere, and phi is the potential developed on the spacecraft surface. So, now I can write I phi again as this equation, I phi is equal to I 0 and multiplied by this, where the I 0 is when there is no spacecraft is not charged. Spacecraft is not charged means phi is equal to 0, spacecraft is not charged. Okay. So, again, so then you will have the I 0 is equal to this term, this term will be your I 0. Oh, sorry, excluding A, this term. Okay. So, you are writing that I 0 is equal to twice pi A n q V L, and whenever you are considering this, when this spacecraft gets charged, then the H term will be included. Now, we will consider a plane geometry. Now, you see when you are considering, and here if you consider an infinite plane, the plane is very large. So, whenever it is an infinite plane, so there is no central force, and then there will not be any angular momentum, means there the scale height. So, if when I consider a plane geometry, what does it mean? That it is a sphere whose radius is infinite. So, in that case what is going to happen, or a cylinder of infinite the radius. So, that the symmetry it requires the trajectories to be one dimensional. So, like in when you are considering as suppose a cylinder, then the cylinder is something like a a two dimensional problem. When I am considering the spherical problem, so it is a three dimensional problem. When I am considering plane geometry, it is basically a single dimensional, because here the variation in the, it is only in the plane perpendicular to the plane. So, that is why it is a single dimensional problem. So, in that case what is happen, when is a plane, so my this term should become infinite. So, when it will become infinite, the A h by A will be 0 for A tends to infinity. Okay. So, in so under that condition, this attraction term whatever you derived, it will be given by this I phi is equal to I 0. So, means in this case that whatever we are discussing, the charging, that is not possible, and it will have that whenever you take that the whatever it has accumulated the charge, that is not going to change, it will not. So, it will remain the same, that is why I phi is becoming the I 0, that is the initial condition. So, this part we are going to discuss more in detail, that is the current balance equation. So, what is happening here, we are considering the, suppose I will consider the case of the sphere. So, sphere is, it has accumulated already the negative, all the negative charges because of the low mass of the electrons. So, after that it will repel the electron, it is repelling the electron and it will attract towards it, it will attract the positive charges. So, this is your impact height. So, it is attracting the positive charges. So, this is outgoing current, if I call it I e phi. So, this is the outgoing current. This is the outgoing current, and what will be the incoming current, that will be I. This is the incoming current. Okay. So, at equilibrium, when this equilibrium condition is reached, means this potential is not changing, as we already said when you are comparing the the filling of a tub. So, its level when it is constant, water is coming and water is going out through an outlet. So, in that case we call it equilibrium condition. Similarly, here when the incoming rate, that is the current coming and this positive charges are coming and the electrons going, this balance happen, then the spacecraft it reaches to a potential, it is called the built up potential. So, in that case what I will have, these two current, incoming current and outgoing current must balance. So, in that case what will happen, I phi in fact, I should write in the other way. I phi minus I e phi, that will be 0. But here I am considering this charge direction and the current direction is the same. When it is the electron if it is coming and outgoing, that the sign gets changed. So, that is why I have taken the minus sign here. So, with this I will in our future sessions we will consider, this will be the basic equation, this is called the current balance equation, and that we will derive the expression for the currents. We will consider different components of the currents and we will see this we have taken just a very simplified case. So, we will take more complicated cases and you show that how the spacecraft gets charged and a potential is built up. And so, of course, this is related to the surface charging. We are now considering only the surface of this spacecraft. So, this is known as surface spacecraft charging. So, with this I will end here today, and next we will continue with the same topic and we will discuss more and more complicated cases. Okay, thank you very much.